Thank you. All right. I'll be presenting ABY3, a mixed protocol framework for machine learning. And this was joint work with Payman Mahassal. So machine learning has numerous applications, quite astounding. To name a few that are privacy concerned, such as like facial recognition, genetic testing, and disease prediction, and also fraud detection. All these have a strong privacy component to them in that say we have an existing model and we'd want to evaluate some new user data on using this model, such as your genetic information using some such as 23andMe genetic model. Here, both parties have a strong interest in maintaining the privacy of either the model or their input data. And so this conflict can inhibit the use of these machine learning algorithms in the case of inference. And the problem is only magnified during training, where you have to aggregate together a very large data set to get good models. And so this aggregation of these data sets can also arise privacy concerns. And so in this talk, we're going to sort of use encryption techniques to try to overcome these challenges. So in particular, we're interested in training, and we'd like to be able to combine data from different data sources. So here shown as 3 different data sources. And the goal is that by having more data, we can train a better model. And this is especially true when these different parts of data have sort of different features that sort of complement each other. And so we can leverage this. And so shown here is the data split up column-wise, but we could, in general, our work considers the data arbitrarily distributed between the parties. And as I sort of mentioned, there's strong privacy concerns when you start bringing this data together. And this can either arise from competitive reasons, such as companies don't necessarily want to share their data with each other, or regulatory reasons, such as the case as medical data. And so one obvious question is, can we use encryption to overcome this? And while we can use traditional encryption techniques to encrypt the data at rest and when we're sending it over the network, but all traditional techniques require the data to be decrypted before we can run these machine learning algorithms. And so in this work, we tackle this sort of final step. And to do this, we introduce several new multi-party computation techniques, such as the efficient support for performing fixed point computation, improved matrix multiplication, where we reduce the amount of communication. This turns out to be crucial for machine learning. And then a piecewise polynomial technique that is efficiently evaluated using MPC protocols. And this is really important for machine learning algorithms where they use these nonlinear activation functions, which don't play nicely with traditional MPC protocols. And then to enable all these improvements, we provide conversions between different types of secret sharing schemes, and that's where we get the name ABY. I'll talk more about that later. And building on these contributions, we implement a variety of machine learning training algorithms and inference using logistic regression, or linear regression, logistic regression, and neural networks. And our framework is general in some sense in that you could implement other types of machine learning algorithms on top of it, or non-machine learning algorithms. So to the building blocks. So we, at all points in this protocol, the data will be encrypted. And the way we encrypt it is using a technique known as secret sharing. So here, if we have an input x, we pick 3 random values such that they sum to the original value x. And so each one of these parties, shown here as these companies, will encrypt their data using secret sharing. And then the first party, in this case Visa, will send some set of these shares to each of the other parties. And in this way, it's sort of distributed. And in this talk, we consider several different types of secret sharing. So the first is what we call arithmetic secret sharing. Here, the values are they are summed over some group, such as 2 to the power k, modulo 2 to the power k. We also consider binary secret sharing or Boolean secret sharing, and this has different trade-offs. And then for those who know, we also use Yau's garbled circuit secret sharing, though I won't talk about that, but conceptually it's similar to Boolean secret sharing. And regardless, I'm going to use this sort of x in the box notation to represent that this value x is distributed between the parties in this encrypted format. And one sort of amazing fact about cryptography is that given this, the data is distributed in this way, we can actually compute any function that we want. And in this case, we're mostly interested in machine learning algorithms. So that's what we'll do next. And only the final result will be revealed. To give you a flavor about how this works, say we have some arithmetic secret shares and we want to add two of them together. Well, this is really simple in that you can just add the corresponding shares together locally and get the new share of the sum. However, the case of multiplication is actually more complicated in that you can't just multiply your local shares because you'll be missing these cross products. And so our paper utilizes a scheme known as replicated secret sharing, where instead of each party holding one out of the three shares, they hold two out of the three shares. And then what you can do is take this observation in that each party can compute some, when you expand out the secret shares in this form, each party can compute some subset of the cross terms. And in this way, each party can locally come up with a new local share, Zi, and this can be then, since we're in the replicated secret sharing setting, we have to communicate this to the next party. And this general multiplication protocol is actually of Lindell and Knopf in the audience that we use. And so we build on this basic multiplication protocol. A lot of our machine learning protocols or machine learning algorithms work over the real values. And so most previous techniques for doing MPC only worked over the integers. And so we actually show that you can implement fixed point arithmetics using this secret sharing scheme, where we have say L bits of an integer representing the fractional part, and then above that is the integer part. And so addition normally just naturally works using these fixed point secret sharing, where you just sort of logically separate what each bit means. But when you go to do a multiplication, you actually run into a problem, and this is just true for fixed point arithmetics in general, in that you end up with double the number of fractional bits. And so when you're not concerned about secret sharing or what have you, you can just lop off the bottom and top bits that you're not interested in, and you'll get some rounding error on the bottom, and you might wrap around on the top, but you just assume you're either okay with this or you do something else. And then last year, Mahasel and Zhang showed that you can actually extend this technique of fixed point computation to the secret shared setting. So it's actually not, it was non-trivial to actually how to do this, but they show a scheme to do it. And it introduces an additional small rounding error. That's okay. But one limitation of their approach is that it only worked on 2 out of 2 secret shares. So where there's just like 2 values that you can sum together. And in our case, we have 3 values that you sum together. And their approach actually completely breaks under this new type of secret sharing. And so we show an extension of their sort of basic approach to any honest majority. So you could have even more shares, and our approach still works. And the main idea is that we briefly switch to a sort of 2 out of 2 secret sharing and then switch back. And to do this, we first pre-process a random value R that's a secret shared between the parties. And we come up, then we somehow compute R prime, which is the same as R, but where the bottom L bits are sort of truncated off. And so you can do this using a variety of techniques in the pre-processing phase. And then in the online phase, we do the traditional multiplication protocol as if they're just working over integers. And then we reveal the result, which is subtracted by R. And R sort of acts as a masking variable. And now we're in the situation that we have sort of 2 shares, T and R prime. And now we can use the traditional Mahasel and Zhang approach, where this T is sort of like the first share logically, and this R prime is the second share. And the way we implement this is that you can actually fold this reveal into the multiplication, and so we end up with having almost no overhead over traditional integer multiplication. But now we can support fixed point computations. And this can also be made malicious secure. Our next contribution is for improving matrix multiplication, which is heavily utilized in machine learning algorithms. So here we have X, which is a 2-dimensional matrix, and Y, a vector. And we want to multiply them together to come up with Z. And we can use the sort of traditional matrix multiplication algorithm where you take each row and each column and you compute the inner product. And that gets you the corresponding element in the output matrix. And if you do this sort of just out of the gate, the amount of communication you'll have is proportional to the size of the larger matrix. And communication ends up being one of our main bottlenecks. And so we want to optimize this if we can. And if you go back and recall how that multiplication works, is that first everyone sort of does a local computation where they compute their local share, and then they communicate that share to the next party. And we observe that you can actually compute this local share for all of these matrix terms, this inner product, and then only communicate the final result. You don't have to communicate at every step. And this is sort of actually true in more general case where you want to do some multiplications and then some linear operation. And so that's exactly what we do. We compute a single ZI term for each row and column pair, and then we communicate this once at the end. And this gives us a factor of D less communication. And in the case of machine learning, this can be like 1,000 times less communication. So it really starts to pay off and is crucial for our practical performance. And then the next technique that we introduce has to do with piecewise polynomials. So in machine learning, there's a step in the algorithms where you have to apply a nonlinear function to your current data. And the problem with this is that machine learning or multi-party computation techniques don't play well with like exponentials or some other types of like division, which these activation functions often will use. And so we replace these sort of traditional approaches with approximate versions, which we implement using piecewise polynomials. So here we divide the function. So our target function that we're trying to implement is divided up into like F0, F1, and F2, where there's these thresholds Ti that divide up the regions that we're applying each function to. And we want to evaluate this. And so our strategy will be, we're going to take the sum over. So this middle part is sort of a range query. We test whether it's inside our two ranges that we're interested, from Ti to Ti plus 1. And then we multiply that value with the corresponding function. And we sum up over all of them. And so in the end, only one of these summation terms will be non-zero, which is the range that we're in. And it will evaluate to the polynomial that we're interested in. And so using traditional sort of MPC techniques, we can easily evaluate these polynomials just because it sort of naturally works out, which is great. But then the question is, how do we compute this range query where the boundaries are public, but the value we're checking is private or secret shared? And so the way we do this is that, we actually use sort of two's complement representation of values, and this will come into play in a second. So we take the threshold Ti and we subtract off X. And then we convert this to a binary secret sharing scheme. And in this binary secret sharing scheme, the most significant bit is actually sort of acts as the sign bit. And so by converting to Boolean secret sharing, we can immediately get almost for free the sign bit that we're interested in. But now to do the multiplication with the final Fi polynomial, we need to convert this. Well, we need then apply some logic to check whether we're inside the two ranges, and then convert this back to the arithmetic secret sharing scheme. And so we do some variety of tricks here, and we optimize it significantly, and we end up only requiring log m rounds, where the m is the number of bits that we represent x with. And so it's quite efficient. And once we started doing these conversions, we realized it sort of might be useful to add other types of conversions. And so we show a general way to convert from arithmetic secret sharing to Boolean and then back again. And the general idea that we use is that each party holds some local shares of this value that they are secret sharing. And then they input these into a secondary MPC protocol, which outputs new shares. And we optimize this in a variety of ways and ends up being quite efficient. And in addition, we show conversions from these two types of arithmetic and Boolean secret sharing to this other type, Yau's garbled circuits, which allows you to have lower latency in some settings. So it's another way to trade off if you're familiar with it. And then with that, I'm going to switch to the machine learning applications. And so the most basic sort of classic machine learning algorithm is linear regression. Here, what we're trying to do is given these dots, and we want to find a linear line that goes through them with the smallest amount of deviation between the line and the points. And so we're trying to find a linear function f. And since f is linear, we can express it as the inner product of the input xi's with the corresponding weights for each dimension. And we're trying to find weights that minimize the distance from the target y. And in this case, you can define a cost function and then run an optimization problem. In this case, we use the L2 norm for the cost function. And you can end up running an iterative algorithm where we define the weights as wj is recursively defined as itself minus alpha and then times these other terms. And here, this green part is sort of the predicted value output minus the real label, and that's so your error, and then you multiply it in the direction that your inputs are, and this eventually will converge to your the optimal w. And you just can run this over and over, and we can use our matrix multiplication techniques to efficiently perform these multiplications, and it ends up being very efficient and and practical. We implement logistic regression. Here, it's very similar to linear regression, except for crucially, we apply this function phi to the inner product of here, and this maps the value from a sort of arbitrary value to a 0 and 1, and it's used to classify whether you're above a line or below a line, and it works in classification problems. However, this phi function is this really nonlinear, like it's a division with an exponentiation in there, and these operations do not lend themselves nicely to traditional multi-party computation techniques, but you can probably guess what we're going to do. We're going to replace this nonlinear function with a polynomial. So a piecewise polynomial. So shown here is sort of linear functions, which is just with a zigzag shape, and it gets you a decent approximation. And this is what we actually use in our implementation, and it only degrades the accuracy very mildly. But since we have a general approach, we can also use a more accurate prediction or accurate polynomials or higher degree to get a better approximation. And then we also generalize this approach to neural networks. And effectively, a neural network is, you can think of it as just like something similar to logistic regression, but you recursively apply it when each one of these nodes in this graph is like one of these regression problems where you do a matrix multiplication and a nonlinear function, and you just do it over and over. And there's some other problems that arise, but we solve them in the paper. And so we can do neural networks. And so here is our sort of performance results. So in this case, we're trying to do inference, so prediction. So we're given a handwritten image. Then we want to come up with the corresponding number. And you can use a variety of different models. So shown here at the top is a linear model. And our performance is roughly similar to the previous fastest two-party protocol of secure ML. But really where we show our big difference here is the amount of communication that we have to do. And this stems from just being able to do more efficient operations in our three-party setting versus two parties, and along with our optimizations. But where our approach really shines is in the case of neural networks. And here you can see that we are several orders of magnitude faster than all previous works and require less communication, like 2 orders of magnitude faster. So that's it's one of our main results. And this mainly stems from just trying to optimize all these conversions and really do everything very efficiently in this three-party setting. And then we also look at training. In this case, only other work that did training was the secure ML paper that I was just talking about in the two-party setting. And you can see across the board we're roughly like 700 to 600 times faster, or up to that much, in running time and communication. And so that sort of is all the results. But to summarize, we introduce a variety of new protocols for fixed point computation, so you can perform real values, or improved matrix multiplication, this piecewise polynomial technique, and general conversions between all these different share representations, which allow you to really get after the efficiency of whichever way you can frame your computation. And then we implement a variety of machine learning protocols. So thank you.
5 minutes for Q&A. Please come to the microphone so we can record the questions as well.
Hi. So my question is, SecureML, the experiments that they run with MNIST, they only use zeros and ones. Did you guys use all 10 digits? And what was the accuracy? I maybe missed it on your slides.
Yeah. So for the linear model, I guess they used everything, but for the logistic, or maybe I'm wrong. We used everything.
we asked them and they said only 0 and 1s.
Oh, I think at least in the logistic case, we use zeros and ones because it's just classification of two classes. For the linear model, I think we used all of them, but I don't remember.
Because the accuracy changes significantly.
Yeah, that would make sense. We're almost functionally equivalent to the plaintext case. And so like whatever you can do in a plaintext scenario, you can also do here. Pretty much the only difference is that we use a slightly different activation function, which degrades performance a little, and there's tiny rounding errors, which don't really have an impact. So it's whatever you can do on a plaintext model is about what we can do here.
Okay.
I just have a question with the number of rounds of communication.
Yes.
So in this slide, you just have the kind of total amount, but are you comparable to the other or better than the other?
In terms of rounds of communication between us and SecureML, yeah, it's like equivalent. I think some of our approaches actually use slightly more rounds, but it's sort of optional. These numbers are from the LAN setting where rounds don't matter so much. But yeah, we can match anyone's rounds.
So the communication is much better than the secure ML, and do you think is the major source of improvement?
Yeah, that stems from, so we're in a kind of weaker security model where we're in 3 parties with 1 corruption, and that allows us to do a much more efficient multiplication protocol that I showed you at the beginning. But in the secure ML, they have to do a pre-processing phase where we generate these triples, and that is almost where all their communication is. And they also use garbled circuits more than us, which adds to the communication too.
Okay.
Thank you very much for the presentation. So I'm not in this field. Maybe my question doesn't sound that much right. Do you make an assumption that the data that is shared is equally distributed between the parties? And if this is the assumption, what will happen if there is a very strong imbalance between the parties that they are sharing the data? Does it impact the privacy or not?
Yeah, so some works do make assumptions about how the data is distributed, but we do not. So it could be arbitrarily distributed, like one value from one person, all the others from the other. And in fact, since the data is sort of secret shared between these 3 servers, additional parties can contribute data by first generating the secret shares and then sending it to those 3 parties. So you could have a sort of client-server model where these 3 servers perform a encrypted computation on behalf of other people.
Thank you.
2 quick questions.
Okay. Can you give some more details on the approximation of the ReLU function, for example? What is the degree of the polynomials that you use?
Yeah, so the ReLU function we actually implement exactly. So it's like a 0 below and negatives, and then it's like a linear x equals y line. And so we just set a threshold, one of those says piecewise. So we just have a 0 function, and then we have the x equals y function above 0. And so we can implement it exactly just with 1 threshold.
Okay, so for regression, logistic regression, the formula itself includes an exponential. How do you handle that?
Yeah, so here, let me just go back real quick. So in practice, we just implement this dash line, and so we don't really implement it at all. We completely avoid it and just do some thresholds, and then yeah.
Okay, makes sense. Thanks.
Quick question and quick answer for the last one.
Sure. In SecureML, I mentioned a way of client-aided multiplication triple generate. So what's your cost compared to the client-aided SecureML?
Yeah, we're actually faster. So you can think of the client-aided approach as being in this 3-party setting, except for they use 2-party techniques. So we natively start with 3-party techniques and build up from there, and you get quite a bit of efficiency.
So how's the magnitude?
Oh, like 10x. I don't know. More? Well, it may more. It depends. Like, it could be as much as pretty much it just decreases the communication, and this online time is the difference.
I see.
All right.
Okay, let's
take care.
thank the speaker.